Because if you have too many non-zero terms due to fill-in term, then it will take more computational effort and more computer memory requirement. So for that reason, normally what we want to do will be, if you see on the next slide, suppose I give you the matrix A. This is the main diagonal. And you can see the bunch of non-zero there. There's a zero value there. And let's say I give you the right-hand side vector B. Okay? So that means we want to solve the system equation AX equal to B. You know? Now, without wasting of time, you can say, how do I find out the matrix U, the so-called factorized matrix U, from the given matrix A? Now, at this step, I just want to caution you, all we want to do is to want to find out the symbolic factorization, factorized matrix U. Factorized matrix U. How do we find out the symbolic factorized matrix U? When I say symbolic, what I mean is I don't really care about the actual numerical value. All I care is about a non-zero term after factorization is done. Where are the locations? How many non-zero terms that you will have after you do the factorization? Well, from that, given matrix A shown in equation 31, we can clearly see that using the idea that I presented to you earlier, as you can see at this location right here, which is A at row 2, columns 6, originally equal to 0. Without any calculation, can we tell the factorized matrix symbolic factorization at the same location U26? Will that equal to 0, or will it be different from 0? Well, the answer to that question is very obvious. If you want to find out U26, you just look at column 6, that we have right here, and we look at column 2, that we have right here, column 2. And then because you see the product of this term times that term is non-zero, that means the summation of the so-called UKI, UKJ that I talked earlier will become non-zero. And therefore, we know for sure U2x will not be 0. So for that reason, we have a fill-in term in here. And then similarly, we can identify very easily these two zeros that you have from the beginning, from the matrix A. After we do the symbolic factorization, we know that it will become non-zero due to the fill-in term. And similarly, these two zeros here will become non-zero, so we call fill-in term. This 0 here will become non-zero. Obviously, this term, let's say number 5 in here, is non-zero. After you do the symbolic factorization, it will also become non-zero with a different value. But again, we don't care about the actual value. So what I'm trying to tell you is this. If you immediately factorize the matrix A given to you, then based on the symbolic factorization, we can see that the matrix U will have, let's say, 1, 2, 3, 4, 5, 6 fill-in term, non-zero, in the upper portion of the matrix U. And that is maybe too much. So the idea here is there any way we can manipulate the given matrix A such that after you do the factorization, either symbolically or numerically, the number of fill-in term F will be reduced a lot. That's what we want. And the answer turned out to be, yes, there's a way to do that. So, and let me discuss that on the next slide, okay? Let me discuss that on the next slide. Let's see. Well, it turned out that as long as you know the so-called non-zero location of the original matrix A, there exist several algorithms that will use that given matrix A is the input, and then the output of that so-called algorithm that you don't need to know now will be an integer mapping array, which we call I-perm of the new equation is equal to the old equation. So let's say for the given matrix A that we have in equation 31, go through some reordering algorithm, such as reverse Cuthill-McKee algorithm or METiS algorithm, reordering algorithm. Any of those algorithms available, they will give you an integer mapping array we call I-perm of new is equal to old. So what does that mean? And what we are going to do with that information? The idea here is, you see, this I-perm of 1 is equal to 6. That means the old equation number 6 will be swapped with the new equation that we call it equation number 1. Similarly, the old equation number 5, that will be swapped with the new equation number 2, and so on, so on, so on. So make use of that kind of algorithm. What happening is, you can go back to the previous slides. The given matrix A with a bunch of non-zero value like that, all of those non-zero value like 112, 110, 4, 3, all of those non-zero value will appear at a different location in the new matrix, which we call A star. Okay, at a different location. So, as an example, you take a look. Let's say we have this value number 5 right there, number 5. And it occurs at location what? At the old location, row 2 and column 3. That is the old location. Now, let's see what happened to this value number 5 in the new location, okay? The old row 2, column 3. Is that right? That's what we said, right? Yeah. Old row 2, column 3. Based on this information, the old row 2, right there, now will become the new row 5. So the old row 2 now become the new row 5. Similarly, the old column 3, right here, will become the new column 4. So this will become the new column 4. And therefore, as you can see, that value number 5 here, that used to be resided in location row 2, column 3, now it will move to the new location row 5, column 4. Row 5, column 4, which is right here. So, for the same idea, what I'm trying to tell you is through equation 35, which is the mapping between the old equation number with the new equation number, or the mapping between the old row number with the new row number, or the mapping between the old column number with the new column number. Through this equation 35, the mapping, we will be able to move all the non-zero in the original matrix A into the new location. And that new matrix there, we call it matrix A star. For the same idea, all the non-zero value occur in the given vector B will correspondingly move to the new location in the vector which we call B star. So, what does that mean? What it means is, instead of solving the original system AX equal to B in order to solve for the unknown X, we prefer to solve a new system, which we call A star times X star equal to B star. And like I told you in the previous slide, we know how to get the new matrix A star using the mapping integer array I-perm. We know how to get the new right-hand side vector B star, and therefore we can solve for the new unknown X star using the same familiar procedure like Cholesky method or LDL transpose algorithm. Now, the advantage by doing that is this. If you use the new system 38 right here and you use Cholesky, well, then we can see that for the new modified matrix A star like this, if you want to factorize this new matrix A star, then the number of fill-in terms you introduce in this case turn out to be only 1. That means computational effort to solve the new equation 38 will be a lot less than the computational effort to solve the original equation, which is AX equal to B. Okay? So now, after explaining to you that, here's the next one. The process to change the old equation or the row or the column, the old system, into the new equation or new column or new row, that process is just like swapping an old equation to become the new equation. In this kind of scheme, you as a student supposed to know how to swap. Let's say the old node 6 become the new node 1, or the old row 5 become the new row 2, or the old column 4 become the new column 3. That process is like swapping one node to another node. And that can be explained again by going through the game which I showed you in the very first slide. All right? So if you take a look at the first slide, you can see this kind of game available on the internet website. So